Spend precision where it matters, let go where it doesn't. It sounds like advice for artists, but it's also a law of good engineering whispered by physics. Nature is selective crystals form with atomic neatness, then break with casual grace. Hearts keep microsecond timing, then hand the rest to elastic arteries and pressure waves. If we copy that pattern tight, where outcomes hinge loose where they don't, we get humane efficiency. We spend care on what touches people's bodies and minds, and we relax where mere numbers would distract us from what truly matters. Begin with heat, because the story of civilization is the story of controlled temperature. We bake, we pasteurize, we forge, we stay warm and cool. Too often we use high-grade energy electricity or flame to do low-grade work, like nudging room temperatures. The physics rescue is the heat pump, a device that doesn't make heat so much as move heat smuggling thermal energy from a colder reservoir to a warmer one using a little electrical work. The key measure is COP, the coefficient of performance heat move, divided by work input, and under small temperature lifts it easily exceeds 3. That's not magic, it's Carnot. The smaller the temperature difference you push against, the less work you need, which is a design hint as crisp as any blueprint. So we sculpt differences. We insulate because the cheapest watt is the one you never need. We run low temperature radiators or underfloor loops because a 40-degree loop demands less effort than a 70-degree one. And we choose heat exchangers with generous surface areas to trade heat with soft, forgiving gradients. Precision goes into sealing air leaks and right-sizing compressors because short cycling is both noisy and wasteful. Looseness is fine for the width of a thermostat band when no one's home. The physics rewards this humility. Small lifts, big gains. Big lifts, small gains. Spend precision where gradients bite. Let go where inertia can carry you. Zoom from one house to a street, a campus, a district. Cities are thermal ecosystems. Bakeries reject oven heat. Ice rinks and data centers dump warmth while making cold. Apartments want gentle evening heat. Hospitals want high temperature sterilization. Offices crave midday cooling. If each building fights its own thermal battles, we pay the gradient tax again and again. Tie them together with a district loop, a medium temperature water circuit, and the picture changes. One building's waste becomes another's resource. Each heat pump only needs to nudge temperatures up or down a little. The vocabulary here is exergy use, high exergy sources for high exergy tasks, and low for low. It's common sense quantified. Think of the loop as a temperature ladder. At the top, processes that need genuinely hot water or steam sterilization, some industrial cleaning. Below that, domestic hot water. Below that, space heating for well-insulated buildings. At the base, space cooling that trims the last warmth before the loop releases a modest remainder to the environment. That sequence is a graceful cascade. We spend modeling effort at the top, matching real needs to high-grade sources, and then simplified downstream, so valves and pumps can be robust, understandable, and quiet. Grace matters. A system people can understand is a system people can love. A system people can love is a system they'll maintain. Time is a dimension we often forget to engineer. Thermal mass is storage-free, quiet, and hiding in plain sight. Concrete slabs, water tanks, even books and furniture absorb and release heat with hours-long time constants. If a district loop nudges heat into the mass at midday, when renewable generation is plentiful, evening warmth arrives with little additional work. Phase change materials add a gentle superpower. As they melt or solidify near room temperature, they soak up or release a lot of heat with barely any change in temperature. We spend precision on choosing the right melt point and the right charge-discharge window. Then we let go of per room micromanagement because a good buffer smooths the day's bumps. Humane efficiency refuses the false choice between comfort and conservation. People perceive warmth as much with their skin's radiation balance as with air temperature. A warm floor can let air be 2 degrees cooler without anyone feeling chilled because the body trades heat by radiation with surfaces as well as by convection with air. We tighten radiant design surface temperatures. Glass with low emissivity drafts minimize while relaxing on the last decimal place of air set point. Noise matters too. Compressors that hum softly, fans that breathe rather than howl ducts that don't whistle. The person who tries to sleep through a rattling grill will not thank your spreadsheet. Physics tells us where comfort actually lives. Ethics tells us to center it. Now bits. Moving information is a thermodynamic act. Switching transistors dissipate, energy wires resist, radio links smear and fade. Edge computing accepts those facts and keeps decision-making near where data is born. Motor drives want microseconds. Cameras for pedestrian safety want milliseconds. Dashboards for weekly reports can wait seconds or hours. We spend precision on tight local control loops, and we let non-urgent analytics batch and nap. The metric that helps us steer is inferences per joule, the computational cousin of miles per gallon. A model that's 10% less accurate but 3 times more efficient may be the ethical winner when it's embedded in a battery-powered device serving a school or clinic. There are practical levers here. Quantization trims the bits used to represent numbers, 8-bit or even 4-bit arithmetic for neural networks, so multiplications cost less energy and memory traffic shrinks. Pruning removes weights that barely change outputs. Distillation trains smaller student models to mimic bigger teachers for deployment at the edge. We spend validation effort ensuring safety-critical performance doesn't degrade. We let go of maximalist benchmarks that impress slides but don't affect real users. Event-driven wake-ups beat constant polling. Caching intermediate features near a sensor beats streaming raw data to a cloud. The shortest distance between sensing and acting is not just faster, it's kinder to the battery and to the grid. When energy and computation meet, the synergies can be engineered rather than hoped for. Data centers produce low-grade heat steadily. District loops can harvest it with heat pumps doing modest lifts to make it useful for space heating or domestic water. In return, district operators can offer demand response, shifting thermal loads to hours with abundant renewables to help data centers schedule their batch jobs. We can even co-site small server rooms with municipal pools or clinics, using their waste heat as a civic asset. The control brain for such a system need not be monolithic. A central scheduler sets broad goals. Building level controllers make quarter-hour decisions. Device controllers run low latency loops. Spend precision at the top, clear optimization goals, safe constraints, and at the bottom, deterministic control, secure fail-safes. Let go in the middle. Use simple heuristics that are easy to audit and fix at 2 in the morning. 2 in the morning matters. Maintenance is the unseen half of ethics. A humane system lets a tired technician succeed on the first try. We label valves so a newcomer can trace flows. We mount differential pressure gauges where they can be read without ladders. We print a one-page schematic and bolt it to the wall. We choose open protocols so tomorrow's replacements can talk without a proprietary translator bot. In computing, we make firmware updates atomic and reversible. We log locally so diagnosis survives a network outage. We keep a console port accessible. Precision belongs in safety margins and rollback plans. Looseness belongs in stylistic flourishes that nobody in distress can afford to decode. The numbers can sing when we arrange them to. Consider a winter loop at 30 degrees Celsius. Well-insulated apartments might need only 40-degree water for comfortable radiators, just a 10-degree lift. A heat pump operating across 10 degrees can achieve a COP above 3 quite comfortably. The same machine forced to lift across 30 or 40 degrees will fare far worse. Domestic hot water at 55 degrees sits higher on the ladder. We lift it only in bursts, then sequester it in a well-insulated tank. Meanwhile, a grocery store's refrigeration rejects heat back into the loop, lowering the grocer's electrical bill because its condenser no longer fights hot outdoor air. 10 small design kindnesses compound into one large quiet gain. We should talk about control philosophy because the shape of control is the shape of dignity. A graceful cascade sets crisp objectives at the top, keep indoor operative temperature in a generous band tuned to human comfort, minimize return temperature on the district loop, guarantee latency under a strict bound for safety critical inferences, maximize inferences per joule for routine classification. Those objectives become policies. Preheat thermally massive zones when renewable power is abundant. Prioritize dehumidification when summer humidity spikes to protect perceived coolth. Widen set points when spaces are unoccupied. Finally, policies drive actions that are deliberately simple. Bump a valve by a few percent, adjust a pump speed by a small increment, wake a microcontroller on an event edge, then let it doze. We spend intellectual precision at the objective layer. We gift simplicity to actuators where gears and fans live. Edge cases define character. Heat waves and cold snaps, brownouts and network outages, they are when designs meet reality. Humane systems degrade gracefully. They keep ventilation running, even when fancy heat recovery must pause. They hold a modest thermal reserve for long weekends. They permit manual overrides that are obvious and physical. In computing, they sandbox faults, so a failing camera does not collapse the traffic grid. They roll out updates in stages with easy rollback. They phone home politely, not incessantly. The strictness lives in the rails that keep people safe. The softness lives in the cushions that make temporary imperfection bearable. There's a life cycle horizon to keep in view. Embodied energy and materials can dwarf operational tweaks when we choose poorly. A slightly lower COP paired with a durable low-leak refrigerant may beat a headline COP tied to a fragile high-impact fluid over the life of the machine. A steel pipe you can re-insulate and reuse in 40 years may be greener than a composite with tricky end of life. We design for second lives heat pumps with serviceable compressors, control boards with standard connectors, sensors you can replace with a screwdriver. On the compute side, models should be updatable without replacing hardware. Accelerators should support multiple numeric formats, so they age gracefully. The planet notices what happens after the press release. Trust is a performance metric. When residents understand why their home feels calm, the bakery's ovens warmed your block this evening. Your building released the heat. It's stored at noon. They accept small deviations like a 5-minute preheat because the story makes sense. Dashboards that show radiant surface temperatures along with air temperatures teach true comfort physics. Little indicators that pulse when the grid is green let people feel part of a bigger choreography. We spend precision on honest, legible communication. We let go of gamified dashboards that exhaust attention without improving outcome. Now a final pass through the core themes tight where they matter, loose where they don't. For heat pumps, be strict about temperature lift, refrigerant stewardship and acoustic comfort. Be relaxed about ultra-tight set points no one can feel. For district energy, be strict about loop temperatures, exergy matching and simple hydraulics. Be relaxed about obsessing over perfect load forecasts when thermal mass is forgiving. For edge computing, be strict about real-time constraints, model right-sizing and sleeping, often to raise inferences per joule. Be relaxed about vanity metrics and unnecessary cloud round trips. We aim for systems that are quiet, repairable, legible systems that make people feel looked after, not managed. If you want a field test, ask 2 questions at the whiteboard. First, where does physics say the leverage is largest? That's where you budget precision gradients, latencies, safety margins. Second, if someone who has never seen this system has to care for it at 2 in the morning, can they succeed? That's where you trim cleverness and choose parts that are obvious, labelled and forgiving. The universe prefers gentle slopes and well-timed pauses. When our designs do too, comfort emerges as a property of the whole, not a battle fought in each room or each rack. And so humane efficiency is not a spreadsheet trick, it's a temperament. It's the willingness to ask what people actually feel and need, then align physics and code to deliver that with a minimum of drama. It's the patience to let thermal mass do its slow work while fast control loops do theirs. It's the humility to nap at the edge, to whisper, rather than shout with pumps and fans, to trade a little neatness on a graph for a lot of calm in a home. Spend precision where it matters, let go where it doesn't. We build machines that move heat like kindness moves through a neighborhood quietly, efficiently, and with care. Let's ground this ethic in the grain of matter, start at the copper windings and carbon molecules, because humane efficiency only becomes real when it inhabits materials. A heat pump is not a slogan, it's a vapor compression cycle playing a 4-act drama through a working fluid. In the evaporator, low-pressure refrigerant boils, stealing latent heat from the source. In the compressor, it is squeezed, its temperature leaping. In the condenser, it rains out heat into your loop. And at the expansion device, it relaxes pressure and temperature falling to begin again. We spend precision where phase change actually occurs, superheat at the evaporator outlet, subcooling at the condenser outlet, and the proper mass flow set by an expansion valve that tracks load. We can be looser about the last decimal place of loop flow because thermal inertia will smooth what control theory calls small signal fuss. Temperature lift is destiny for COP, so we design so that the lift is small most of the time. That means the emitter's radiant floors, fan coils, oversized radiators deserve care. The larger the effective area, the lower the supply temperature needed for comfort, and the happier the physics becomes. It's the same with source side design. If you can draw from a temperate, an earth loop, a mild exhaust stream, the machine's work is gentler. We We respect return temperatures like a chef respects mise en place. A low return is not a vanity metric, but a promise of easy work for compressors. And we accept that on the rare polar night, the lift will be high. Humane systems have backup immersion heaters or hybrid modes, not for every day, but for dignity when air carries knives. District energy is choreography. So let's talk hydraulics as if we're talking music. Constant volume loops are drummers, variable speed pumps are dynamics, differential pressure sensors are the conductor's ear. We spend precision on balancing and commissioning, on ensuring that terminal units see the head they were promised, because a loop that is out of tune wastes both watts and patience. We can then let go a little on strictly centralized scheduling, trusting each building's local brain to preheat or pre-cool when its occupants actually live their lives, not when a spreadsheet imagined they would. Put simply, central sets, tempo and key, local solos improvise in time. The result is a graceful cascade where upstream assets run steadier and downstream valves only whisper. Exergy is our compass. High temperature steam is a tiger. Use it only when you truly need a tiger. Low temperature water is a cat perfect for curling around radiators and floors. Humane efficiency pairs tigers with surgery and sterilization cats, with comfort and dishwashing. We map uses onto a temperature ladder, then check for chances to step down twice instead of once. A data center's 35-degree exhaust can preheat domestic water to 45, leaving only a modest lift to reach 55. The supermarket's condenser heat can keep a nearby childcare centre's floor warm through winter mornings. We are suspicious of any design that demands 90 degrees everywhere, the way a good musician distrusts a song played fortissimo from start to finish. Now, to the air we breathe, because comfort is not only temperature. Indoor air quality rests on three legs: ventilation, filtration, and humidity control. Ventilation dilutes pollutants, filtration removes particulates, humidity between roughly 40 and 60% feels kind and restrains both static and some pathogen survival. We spend precision on heat recovery ventilators with sensible and where appropriate latent exchange, so fresh air does not cost a fortune. We size filters for low face velocity so pressure drops don't punish fans. We pick dehumidification strategies that decouple moisture removal from brute force cooling. We allow a little looseness season by season, a summer evening's breeze, through an economizer cycle, a winter day's sun admitted for its radiant generosity. The body notices radiation and moisture almost before it notices dry numbers on a thermostat. Noise is energy you cannot use. A compressor shouts when it is fighting a gradient. A duct whistles when velocities are too high for the cross-section. A fan thrums when blades are misaligned. We spend precision on acoustic layout, resilient mounts, smooth elbows with adequate radius diffusers that distribute gently, because quiet is not a luxury, it's a parameter of health. We let go of the temptation to drive fans at heroic speeds, to shave a minute off a warm-up. A slightly longer ramp can be inaudible and more efficient. The paradox of humane efficiency is that it often sounds like nothing at all, a room that simply feels right, a hallway where you hear your own footsteps and not the machinery's impatience. Edge computing lives under the same thermodynamic sky, so let's draw the circuit. Sensors produce streams, local processors compress meaning, actuators take decisions, the cloud orchestrates trends and updates. We spend precision on the loops whose timing defines safety and comfort, a motor drive at tens of microseconds, a heat pump expansion valve at tens of milliseconds, a camera doing pedestrian detection at tens of milliseconds. We relax the telemetry path into batched event-driven uploads because shipping raw video constantly is both wasteful and brittle. Inferences per joule is not only a chip property, it is a system property. Place the first convolution near the lens, prune the model for the scene cache features so you don't rethink what hasn't changed. It's remarkable how far sleeping often and waking only on meaning will carry a battery. Model stewardship is part of humane care. Big models are like big boilers, powerful but seldom necessary at every node. Quantized, distilled models trained to keep the essence while shedding extravagance can meet real-time requirements on modest hardware. We spend precision on the validation set that matches the street corner, factory line or plant room, not a generic benchmark that flatters a slide deck. We allow ourselves to be looser about the last % of average precision when the human visible experience, latency, steadiness, absence of false alarms improves. The goal is decisiveness without drama. Detect the pedestrian nudge, the valve dim, the lights then rest. Control theory gives our ethic a backbone. Proportional, integral derivative controllers, model, predictive control, and simple hysteresis have their places. We spend precision on anti-wind-up feed-forward terms that anticipate load based on occupancy and weather, and constraints that keep actuators within happy regions. We let go of one-size-fits-all tuning. A radiant slab wants long horizons and gentle moves. A variable refrigerant system wants quicker steps with small overshoot. A ventilation fan wants smooth ramps to spare bearings. The graceful cascade emerges when each layer is tuned to its physics, slow plant, medium building loops, fast device loops. It's the difference between conducting with a baton and trying to play every instrument yourself. Resilience is not an accessory. The week-long cold, snap the 3-day heat dome, the night the network disappears. These are the exams our systems must pass. We spend precision on safe failure modes, ventilation that defaults to a protective baseline valves that fail to a known position, thermal reserve sized for a calm hour of bridge time. We let go of brittle cleverness. A building that requires perfect connectivity to heat is an ethical mistake. Local autonomy is mercy. A plant room controller that can run for days from its own schedule, and sensors then gracefully rejoin the district when the fibre blinks back to life, keeps real humans warm, while abstractions argue elsewhere. Materials and refrigerants carry consequences. The working fluids, global warming, potential, the ease of detection, and repair, the safety class, these are part of the ledger. We spend precision on containment, on leak detection that is honest and maintainable, on recovery fittings that technicians trust. We acknowledge trade-offs. Some low GWP refrigerants are mildly flammable, some old standbys are potent greenhouse gases. The right answer varies by scale, location, and code. The humane posture is to choose fluids and designs that minimize harm over the machine's whole life, not just in a brochure snapshot, and to make service straightforward. So leaks are rare and repairs routine rather than heroic. Embodied energy is the prelude to every kilowatt hour you'll ever save. Over-specifying exotic materials for a tiny operational gain can be a net loss to the planet. We spend precision on modularity and reuse pipes. You can re-insulate and keep pumps in standard frame sizes, controls that speak open protocols, so a replacement 10 years hence won't maroon you on an island. We loosen the obsession with novelty. Boring, proven components applied thoughtfully are often the greenest choice. A system that can be kept alive by the people who live with it is a gift to both climate and community. Human factors close the loop. A plant schematic bolted to the wall. A labeling scheme that even a newcomer can follow, a service log that lives on paper and on device. A thermostat that displays operative temperature, air plus radiant instead of only air. These are grace. Notes that add up to trust. We spend precision on interfaces that teach you feel comfortable because the floor is warm and the air is slightly cooler. The bakery across the street contributed heat from 2 until 4. We relax the urge to gamify consumption with confetti and badges. Gentle, honest feedback tied to bodily sense invites cooperation better than scoreboards ever do. Now tie bits to joules with intention. A district loop can publish a simple price or signal that reflects momentary abundance or scarcity green, when renewables are spilling amber, when neutral blue, when storage is charging for a cold night. Edge devices subscribe and react locally, preheat slabs when green coast, when blue, hold comfort when amber. We spend precision on the mapping from signal to action so occupants barely notice the dance. We allow diversity in response so the system avoids synchrony that could cause spike. A neighbourhood that leans, breathes and rests together becomes more than the sum of its meters. It becomes a thermal commons. Finally return to the hook and listen for its physics. Spend precision where it matters, let go where it doesn't. Where it matters, temperature, lift phase, change management, acoustic quiet, exergy, matching tight real-time loops, safe failures. Where it doesn't, decorative decimal places on set points, vanity cloud, round trips, heroically hot loops for lukewarm needs, dashboards that seek attention rather than convey meaning. We aim for inferences per joule that are high because we chose the right problem size. We aim for cascades that are graceful because each layer trusts the next. The measure of success is not just kilowatt hours avoided, it is rooms that feel kind, streets that hum softly, technicians who go home early because nothing broke in the night. And if there is a single practice you can take to the next design review. Let it be this: draw the cascade first. Put people at the bottom: skin, lungs, ears, then emitters and fans, then loops and compressors, then sources and storage, then the cloud if you truly need it. We spend the sharpness of our minds at the levels where one good choice multiplies through every hour of operation. We let gentleness govern the rest. It's how physics prefers to flow. It's how care becomes engineering. It's how humane efficiency turns from a phrase into a place you can stand and feel quiet, steady and right. Let's tighten the weave with hard numbers and clear laws, because humane efficiency isn't poetry alone. It's physics you can compute. The anchor for heat pumps is Carnot's limit. The maximum theoretical coefficient of performance for heating is the coefficient of performance of the Carnot cycle, is equal to the temperature of the hot reservoir divided by the difference between the temperature of the hot reservoir and the temperature of the cold reservoir with absolute temperatures in Kelvin. If your source is 10 degrees Celsius, 283 Kelvin, and your sink is 40 degrees Celsius, 313 Kelvin, the ideal COP is roughly 313 divided by the difference between 313 and 283 is approximately equal to 10.4. Real machines reach a fraction. Seasonal COPs of 3 to 5 are common when lifts are small. We therefore design emitters and loops to keep lifts small, radiant floors that run at 30 to 45 degrees Celsius, fan coils that are oversized for gentle deltas and source temperatures harvested from ground, loops or data center exhaust near 25 to 35 degrees. It's arithmetic that becomes kindness. Every 10-degree reduction in lift often yields double-digit % gains in seasonal efficiency. Phase change is where the cycle earns its keep. Refrigerants absorb latent heat enthalpy of vaporization in the evaporator, so large heat transfer happens at nearly constant temperature, exactly what we want for stable control. The tuning targets are specific: a few Kelvin of superheat at the evaporator outlet to protect the compressor from liquid slugging, and a few Kelvin of subcooling at the condenser outlet to prevent flashing before the expansion device. Expansion valves thermostatic or electronic meter mass flow to hold superheat steady as load changes. We pay attention to log mean temperature difference, LMTD, across heat exchangers and to the product UA overall conductance times area, because bigger UA lets us achieve the same duty with smaller temperature gaps. It's textbook thermodynamics deployed, so rooms feel quietly right. Hydraulics obeys its own stern but helpful law. Pumping power scales with flow and pressure drop and affinity laws tell us that for centrifugal pumps flow, Q scales with speed, N head, H with N squared and power P with N cubed. That cubic term is a lever. We fit variable speed drives, so a modest speed reduction yields large electrical saving. Pressure losses follow Darcy-Weisbach. Delta P equals F times L over D times rho V squared over 2. Smooth pipes, gentle elbows with larger radii and lower velocities cut V squared losses mercilessly. The commissioning step balancing flows, so each terminal sees promised differential pressure, prevents throttling that wastes head as heat in valves. In humane systems, pumps loaf not shout. We let physics do the heavy lifting by lowering resistance rather than muscling through it. Exergy gives us a ruler for using energy at the right grade. Heat near ambient has low exergy, high temperature steam has high exergy. The district loop at 30 to 50 degrees Celsius is thus a low exergy backbone, perfect for space heating and preheating domestic water. We climb the ladder only when necessary. Heat pump lifts to 55 degrees for Legionella-safe domestic hot water. A sterilizer may need 130 degrees steam and gets it from a dedicated high exergy source. It's a use the cat, not the tiger rule you can quantify using high exergy fuel to do low exergy tasks, squanders the capacity to do work. By matching grade to need, we lower both cost and emissions while keeping comfort steady. Comfort itself is physics you can feel. Mean radiant temperature, MRT, often matters more than air temperature because the human body exchanges heat through radiation as sigma times epsilon times area times the difference of temperatures to the fourth power. This is the net radiative heat transfer from skin to surrounding surfaces using the Stefan Boltzmann law, with emissivity epsilon near 0.95 for skin and most interior surfaces. We can lower air temperature by 1 or 2 degrees and keep perceived warmth identical if floors and walls are slightly warmer. Psychrometrics tells us relative humidity between 40 and 60% curbs Some pathogen viability reduces static and preserves mucosal comfort. The PMV divided by PPD model, predicted mean vote divided by predicted percentage dissatisfied from ASHRAE, shows that small changes in airspeed, say 0.1 to 0.2 meters per second, can widen acceptable temperature bands. So we design for radiant surfaces, gentle air movement, and humidity in the kind range. Numbers become niceness. Air quality has measurable levers. Filtration effectiveness is summarized by MERV ratings. MERV 13 captures over 80% of particles in the 0.3 to 1 micron range, which includes many respiratory aerosols. We size filters to keep face velocity low, around 1 to 2 meters per second, minimizing pressure drop and fan energy. Energy recovery ventilators reclaim sensible, and with enthalpy wheels, latent heat, so fresh air doesn't mean thermal penalty. The control is straightforward. Demand controlled ventilation modulates outdoor air based on CO2 or VOC sensors, maintaining indoor CO2 often below 900 parts per million as a rough proxy for occupants. Quiet fans and smooth ducts reduce both noise and energy because turbulence wastes watts. We feed lungs with clean, calm air and let pumps and fans whisper. Thermal storage is engineering's patience. Water's specific heat, about 4.186 kilojoules per kilogram Kelvin, means that a 1 cubic meter tank shifted by 5 Kelvin stores roughly 21 megajoules, about 6 kilowatt hours. We can preheat slabs. Concrete's volumetric heat capacity is roughly 2 to 3 megajoules per cubic meter Kelvin. A practical building can store tens of kilowatt hours invisibly in its mass. Phase change materials add latent storage paraffins melting near 24 to 26 degrees Celsius, store on the order of 100 to 200 kilojoules per kilogram with minimal temperature swing. The control is model predictive when we want to be crisp forecast, outdoor temperature occupancy and renewable availability. Yet we keep local loops, simple hysteresis bands and gentle ramps avoid hunting. So the slow parts move slowly, the fast parts move fast, and the whole is serene. Refrigerants are chemistry with consequences. Global warming potential GWP numbers guide choices. Propane R 290 is roughly 3. Carbon dioxide R 744 is 1 by definition. Newer blends like R32 sit near 600 to 700. Legacy R410A is about 2000. We balance safety classes A1 non-flammable A, 2 litres mildly flammable A3 flammable with building codes and use cases. CO2 transcritical systems excel for supermarkets and water heating in cool climates, leveraging gas coolers and ejectors. Propane heat pumps deliver excellent efficiencies at low lifts, with careful charge management and ventilation for safety. The humane posture is life cycle aware, minimize charge, detect leaks early, design serviceability, so repairs prevent venting, and choose fluids that keep both climate and technicians out of harm's way. We spend precision on containment. We let go of headline cop worship when it conflicts with stewardship. Edge computing is bounded by physics as well. Light takes about 5 microseconds to go 1 kilometer in fiber. A round trip to a distant cloud can add tens to hundreds of milliseconds, unacceptable for motor control or pedestrian detection. We therefore put tight loops near the plant, microsecond scale PWM for drives, millisecond scale inference for safety cameras, tens of milliseconds supervisory control for valves and pumps. The metric inferences per joule is influenced by algorithmic choices. 8-bit quantization can cut, multiply, accumulate energy by multiples versus 32-bit float. Pruning can remove 20 to 80% of parameters with minimal accuracy loss. Knowledge distillation lets a small model mimic a large one for deployment on microcontrollers. We choose event-driven architectures, so sensors, weight processors only on change. Sleeping silicon is the greenest silicon. There's a thermodynamic flaw to computation. Landauer's principle says each bit of erased information dissipates at least K times T times natural log of 2 joules, about 3 zeptojoules at room temperature. Today's systems dissipate far above that limit due to switching, interconnect and leakage losses, but the principle reminds us that unnecessary computation has a physical cost. The system level corollary is compress relevance early. Perform early thresholding or region of interest extraction near the sensor. Avoid streaming raw megapixel frames when a dozen key points suffice. In data centers, PUE power usage effectiveness close to 1.1 is state of the art. Waste heat exits at 30 to 45 degrees Celsius, perfect for feeding low-temperature district loops with small lifts. We align bits and joules, so one system's byproduct becomes another's input. Control stability is math in service of sleep. PID loops need anti-wind-up to avoid integrator runaway during saturation. Feed-forward terms based on disturbance estimates like outdoor temperature or scheduled occupancy reduce error before feedback even acts. We use model predictive control sparingly and where it pays when constraints, valve limits, comfort bands, demand caps matter and forecasts help. Elsewhere, simple hysteresis and dead bands prevent chatter. The time constants matter. Radiant slabs want hours length horizons. Air-based systems are in minutes. Compressors and expansion valves move in seconds. Microcontroller interrupts in microseconds. So we layer control by physics, not by organizational chart. And we test failure modes deliberately. What happens when the network drops, the sensor lies, or the sun arrives early. Acoustics admits calculation too. Sound power scales with turbulence and mechanical imbalance. Doubling fan speed raises sound power roughly by 6 decibels and often more in ducts as flow becomes more turbulent. We choose larger ducts to halve velocity, which can drop pressure and noise dramatically. We align fans to avoid blade pass tones in sensitive bands. We mount compressors on isolators with tune stiffness to push resonances below audibility. The outcome is measurable bedrooms below 30 decibels, A-weighted at night classrooms below 35 plant rooms, isolated to protect neighbours. Quiet is not an accident. It's a solved equation with human benefits. Envelope physics sets the stage for everything inside. Thermal conductivity, K of still air, is about 0.025 watts per meter Kelvin. Mineral wool sits near 0.035 to 0.045. Polyurethane foams near 0.02 to 0.03. We target low U values overall conductance by combining insulation with thermal bridge-free details. Triple glazing with low emissivity coatings can drop center of glass U values below 0.7 watts per meter squared Kelvin, while keeping interior surface temperatures close to room air to improve radiant comfort. The air tightness metric N50 air changes per hour at 50 pascals guides infiltration control. Getting from say 5 to 1 air changes per hour can cut heating loads sharply and stabilizes humidity. So the heat pump works against smaller lifts and the district loop flows more gently because the building asks less. Verification closes the loop between promise and reality. We commission with functional test step set points and watch responses. Log supply divided by return temperatures and flows to compute delivered kilowatts. Measure electrical input to compute live COP and seasonal performance factor. We use calibrated RC resistance capacitance models of zones to infer envelope heat loss from natural experiments, cold morning sunny spikes, and we update control parameters accordingly. The ethic is humble empiricism, measure, compare, adjust. No theatrics, just truth-seeking that makes tomorrow quieter than today. We then document in language a midnight technician will understand, plain schematics, set point ranges, reset curves, and if X then Y playbooks. Finally, knit energy and computation into a graceful civic dance. A neighborhood publishes a simple 3-color signal based on local renewable surplus and loop temperature green for charge, thermal mass amber for hold, blue for coast and protect. Edge controllers subscribe and translate signal to action with site-specific rules. We avoid lockstep by randomizing start times and limiting ramp rates. We protect comfort with minimum and maximum operative temperatures. We log the small victories, kilowatt hours, shifted decibels, avoided complaints prevented. The design review becomes a checklist aligned with physics. Is the temperature lift minimized? Are hydraulic losses small? Are control time constants matched to plant? Are inferences per joule high because models fit tasks? Failure mode safe and sleepy. So the slogan becomes a system, the system becomes a feeling, and the feeling calm, clean, legible becomes home. Spend precision where it matters, let go where it doesn't. That's not just a hook, it's a map with coordinates. We mark the hotspots, Carno, limits, LMTD, Darcy, Weiss, Buck, PMV, Landauer, PUE. We mark the gentles, radiant floors, dead bands, low velocity ducts, batch telemetry, sleeping silicon. Follow that map, and you will find the same destination in many guises: higher COPs, lower bills, quieter rooms, steadier grids, kinder maintenance at 2 in the morning. It's physics as care, computation as courtesy, and design as an act of empathy, written in numbers that add up. Here's your passage rewritten, so every formula is crystal clear for voiceover. I've kept your tone and the gentle stammer, and I've spelled out each equation exactly as you'd want to read it on mic. Let's step even closer down to the molecules, the electrons, the photons that carry both heat and thought, because the deeper we go, the clearer it becomes that humane efficiency is simply alignment with nature's grain. The universe, after all, runs on gradients. Where there's a difference, temperature, pressure, concentration, potential, there's flow. And every flow wants to flatten, to equalize, to rest. That resting tendency is what thermodynamics calls equilibrium, and everything we build either fights it or works with it. The secret of design that lasts, that feels calm, is to align our technologies with the flows that already want to happen. Start with conduction, convection, radiation, the three basic ways energy moves. Conduction is atoms passing vibrations along their bonds, heat moving through stillness. Convection is heat carried by motion, as warmer, less dense fluid rises and cooler, denser fluid sinks. Radiation is photons, packets of electromagnetic energy leaping through space, not needing matter at all. The Fourier law of conduction tells us Q equals minus K times the gradient of T. Read it clearly, Q equals minus K times del T. The rate of heat flow Q is proportional to the material's conductivity K and the temperature gradient. We spend precision here selecting insulation that keeps K low and detailing joints that keep the gradient of T smooth with no sharp bridges that leak warmth. But we let go of perfection. No house needs to be a thermos. A building that breathes gently through controlled ventilation often performs better than one sealed too tightly and then gasping for air. Convection's where heat pumps dance with air. The Nusselt number ties together conduction and convection. Nu equals H times L divided by K. Read it as nu equals HL over K. It tells you how much more effective convection is than pure conduction. The higher the airspeed and the more turbulent the boundary layer, the higher the nu, and thus the better the heat transfer. But turbulence costs fan power, which scales roughly with velocity cubed. We spend precision on the geometry of coils and fins, optimizing the fin, spacing the Reynolds number range, so that air moves efficiently through picking up or shedding heat with minimal pressure drop. We can then afford to let go of high velocities that make noise and consume watts. Smooth laminar calm replaces frantic movement, and efficiency feels like quiet. Radiation is subtle, but radiant exchange defines comfort. Every surface emits, according to the Stefan Boltzmann law, E equals sigma times epsilon times t to the fourth. Read it as E equals sigma epsilon t to the fourth. Human skin has emissivity around 0.95, nearly a perfect black body in the infrared. A window with a low E coating reflects long-wave infrared back inward, keeping bodies feeling warm even when air temperature is lower. The power of T to the fourth means small temperature differences matter enormously. Raise a wall's inner surface by just 2 degrees Celsius and radiant comfort rises enough to lower air temperature 3 degrees, saving roughly 10% of heating energy. We spend precision on surface emissivity, glazing coatings, and radiant panel layout. We let go of obsessing over fractional air degrees on thermostats because the body's sensors, the skin, the hypothalamus, care about the combined field of radiation, convection, and humidity, not isolated numbers. Humidity connects energy and biology. The latent heat of vaporization for water is about 2,400 kilojoules per kilogram, meaning evaporation or condensation moves vast heat at nearly constant temperature. We spend precision on dehumidification coils that maintain dew points around 10 to 12 degrees Celsius, enough to hold indoor relative humidity near 50% in summer. We design condensate drains to recover some of that coolth or even reclaim latent heat through enthalpy wheels with polymer membranes that exchange both heat and moisture. But we let go of chasing perfect constant humidity. Human comfort tolerates a range. What matters is to avoid extremes that parch skin or foster mold. The air's invisible water cycle becomes part of the gentle cascade. Electricity, our finest form of energy, is both the servant and the measure of our care. Joule's law says P equals I squared times R. Read it cleanly, P equals I squared R. Resistive losses rise with the square of current. High voltages lower current for a given power, so distribution efficiency improves. That's why district systems use medium voltages for pumps and why data centers run 12-volt or 48-volt DC buses inside rack. We spend precision on conductor sizing and power factor correction because wasted reactive power does no useful work. We can then let go of the compulsion to over-specify copper everywhere. Sometimes aluminum conductors properly sized yield the same resistance with less embodied energy. Precision, where electrons heat metal. Forgiveness, where the field is already smooth. Now think of entropy, the great equalizer. The second law of thermodynamics states that total entropy never decreases in a closed system. Every process that concentrates orders, cools or compresses must spill disorder somewhere else. A heat pump's compressor warms the surroundings while cooling your living room. A computer's logic gates expel waste heat proportional to the bits they flip. Humane efficiency doesn't pretend to beat entropy. It designs the spill so it lands somewhere useful. Waste heat from computing warms water. Waste cold from cryogenic processes chills air. The ideal system is a loop, not a line. We spend precision on finding these couplings, the thermal symbioses. We let go of isolated machines that fight alone. Materials themselves encode physics lessons. Copper's thermal conductivity is about 400 watts per meter Kelvin. Stainless steel's is 16. Still air's 0.025. The gap between them is an instruction manual. Mix good conductors where you want even temperature, poor ones where you want isolation. In heat exchangers, we spend precision on wall thicknesses and fin patterns that maximize area while minimizing pressure drop. In insulation, we use multi-layer foils that reflect radiation as well as slow conduction. In phase change slurries, we use microencapsulated waxes suspended in water to combine high heat capacity with pumpable flow. The numbers make design an act of listening. Every coefficient is a whisper of how atoms behave. The flow of fluids follows Navier-Stokes complex, but forgiving if you respect scale. Laminar flow at low Reynolds numbers, read it as less than about 2,300 is orderly. Turbulence beyond that becomes chaotic but increases mixing. We choose Reynolds regimes deliberately. Inside microchannels of a heat pump's evaporator, we want turbulence to spread refrigerant evenly. In long district mains, we want near laminar flow to minimize friction. The pressure loss per meter depends on the friction factor F, which itself depends on surface roughness and Reynolds number. If you want the classic expression, say it aloud as delta P equals F times L over D times rho V squared over 2. Smooth polyethylene pipes with roughness on the order of a few microns keep F small. We spend precision on joints and welds that maintain that smoothness. We let go of mirror polish fantasies that add cost without measurable gain. Smooth enough is perfect. Even computation follows energy's laws. A transistor's switching energy scales roughly with capacitance times voltage squared. Lower supply voltages and smaller capacitances, thanks to nanoscale fabrication, mean less energy per operation. Yet, as we pack billions of transistors, leakage and data movement dominate. Moving a bit across a chip can cost hundreds of times the energy of flipping it in place. We spend precision on locality caches, on-chip memory algorithmic reuse to minimize movement. We let go of gratuitous data shuffling. The limit land hours bound is K times T times natural log of 2. Say it clearly, K times T times ln of 2. At room temperature, it sits around 3 times 10 to the minus 21 joules per bit. Current chips operate thousands of times above that. There's room to fall gently toward nature's floor. In buildings, we can map all these micro laws into one macro picture. The energy balance equation, Q dot in minus Q dot out equals C times dt by dt. Read it as Q dot in minus Q dot out equals C times the time derivative of T. Here C is the building's thermal capacitance. Steady comfort means dt by dt equals 0. Humane control means letting T drift slowly within bands so the derivative stays small and the need for quick corrections vanishes. We spend precision on insulation and sealing that stabilize C. We let the temperature meander within half a degree or two, trusting human adaptability. In effect, we design not a thermostat, but a climate-stable slow soft. Lighting too obeys humane efficiency. The luminous efficacy of LEDs now exceeds 150 lumens per watt. Older incandescents gave about 15. But color rendering index and spectral power distribution matter for perception. Blue heavy light at night suppresses melatonin. Warmer spectra promote rest. We spend precision on spectral tuning and control timing. Human circadian cycles are physics plus biology. We let go of the last lumen when the goal is calm, not stadium glare. Photons are cheap, serenity is not. Acoustics, we recall rides on pressure waves. The sound power level relation is L sub W equals 10 times log base 10 of P over P naught. Read it smoothly, LW equals 10 log base 10 of P over P naught. Doubling acoustic power raises level by 3 decibels. Fans, pumps and compressors add up logarithmically, not linearly. We spend precision on decoupling mounts, on flexible connectors, on path length that allows dissipation. We let go of cosmetic covers that only hide noise instead of removing it. Silence is design expressed as physics fulfilled. Now zoom back out to the planetary scale, because humane efficiency aligns our micro choices with macro flows. Earth absorbs about 1.74 times 10 to the 17 watts of solar power, reflected partly by albedo, emitted back as infrared. The global average temperature balances when incoming equals outgoing radiation. A 1% change in albedo can shift equilibrium by a couple of watts per square meter, enough to warm or cool climates. Our buildings and cities collectively alter albedo and thermal inertia. Light roofs reflect, dark pavements absorb, trees transpire and cool through latent heat fluxes. We spend precision on surface choices, high albedo coatings, green roofs, permeable pavements that breathe. We let go of asphalt maximalism that treats cities as black bodies. Physics at the planetary scale is the same as physics in a heat pump. Gradients, flows, balance. District energy loops extend this planetary thinking locally. The total exergy destruction in a system can be voiced as E dot sub D equals T naught times S dot sub general. Read it cleanly, exergy destruction rate equals ambient temperature times the rate of entropy generation. By sharing heat among buildings, we reduce S dot subgen. The entropy generation in one process becomes input for another. A data center's 35-degree exhaust can feed a nearby greenhouse where plants thrive near that temperature. We spend precision on matching flow rates and temperature deltas so both sides operate near their optimal delta T. We let go of single-purpose plants that waste perfectly serviceable warmth into the air. The second law doesn't forbid reuse, it demands it. When computing joins the loop, it becomes an ecology of electrons. Edge devices gather data, but raw data is heat waiting to happen. Processing it near the source turns some of that waste into action before it cools into entropy. The metric inferences per joule becomes a way of measuring order restored per energy spent. We can calculate a typical neural inference on a modern accelerator might consume about 1 millijoule, multiplied by billions per day, and optimization matters. Pruning 50% of operations saves kilowatt hours, enough to heat water for a shower. The link is real, information is physical. Humane efficiency thus closes a circle that begins with the atom and ends with empathy. Every law, Fourier, Carnot, Navier, Stokes, Landauer, has a human echo. Low gradients mean comfort, smooth flows mean quiet. High inferences per joule means smarter devices that sleep longer. Small entropy generation means longer life for both machines and planet. We spend precision at the joints where physics meets feeling interfaces, transitions, boundaries. We let go of the false idols of control for control's sake. The result is a world that runs cooler, calmer, truer to the equations that built it. And maybe that's the heart of it. The equations themselves are humane if we listen. They whisper balance, proportion, patience, spend precision where it matters, let go where it doesn't. The molecules already know how. We are just learning to follow their lead. Let's bring all these threads into an even more concrete architecture. An architecture you could actually build in a neighborhood, in a campus, even in a mixed-use Vietnamese city block, and watch how physics, control, and care reinforce one another. We'll walk it from source to sink, from joules to gestures, from sensor to sleeper, and we'll do it slowly enough that every law has time to breathe. Picture a district loop running at 35 degrees Celsius supply and returning at 28. That's a modest low exergy spine, warm enough to be useful, cool enough to harvest from many sources. Why 35? Because many high-performance buildings with floor heating or large area fan coils can deliver comfort with supply water in the low 30s. The smaller the delta between source and sink, the closer our real COP can approach the Carnot ideal. Remember, the read aloud C, OP sub Carnot equals T hot divided by parentheses T hot minus T cold close parenthesis. If our loop is at 35 Celsius, call that 308 Kelvin, and we only need to lift to 45 Celsius, 318 Kelvin, for domestic hot water preheat, then say it 3 minus 1 minus 8 divided by parentheses 3 minus 1 minus 8 minus 308 close parentheses equals 31.8. That's the ideal. Real machines at that gentle lift might do 3 to 5. We spend precision on keeping that loop narrow, on not letting it creep upward because someone oversized a radiator or insisted on scalding hot outlets. We let go of the habit of designing everything for 70 degrees just in case, because just in case often taxes the system forever. Where does the heat come from? Several places at once. A data center in the basement of a municipal building rejects at 30 to 35 degrees. A supermarket's condensers run at 30 to 40. A small cluster of air source heat pumps using morning air that's still 24 degrees can top the loop off. A solar thermal array at 40 to 50 feeds in when the sun is generous. We connect them all through plate heat exchangers sized with decent UA so they can operate with 5-degree approach temperatures instead of 15. The lower the approach temperature, the more easily we can use their output. And because every connection has sensors, supply, return, flow, we can estimate harvested kilowatts in real time with Q equals rho times CP times V dot times delta T. Read it cleanly, Q equals rho CP V dot delta T. Water's density near 1,000 kilograms per cubic meter. Specific heat about 4.2 kilojoules per kilogram Kelvin. Multiply and you have truth. We spend precision on those meters because good metering is good manners in a shared system. We let go of micromanaging every flat's radiator valve from a distant server. Distribution is a hydraulic story. Our main loop is primary constant flow low head. Secondary loops in each building pull through variable speed pumps set to maintain a differential pressure across that building's heat exchangers, say 20 to 30 kilopascals. Why variable speed? Because by the affinity laws, if we drop pump speed to 80%, power drops to roughly 50%. We place differential pressure sensors at hydronic ends, the hydraulically farthest points, so the pump knows what reality is, not just what's at the plant. We spend precision here, sensor placement, PID, tuning balancing valves. Then we let go on tiny fluctuations. A 1 kilopascal wobble is not worth a pump surge. Smooth over fast, stability over twitchiness. Inside each building, emitters fit people. In apartments, radiant floors or low temp radiators. In clinics, fan coils with good filtration MERV, 13 if possible. In offices, chilled beams or radiant ceilings, since they work wonders with low temperature water for cooling and slightly warm water for heating. All of those are happiest with narrow temperature spreads and steady flow. That's exactly what our district loop offers. We spend precision on dew point control for chilled beams because running a beam below room dew point causes condensation. Say the psychrometrics out loud, 26 Celsius and 60% RH dew point is about 17 to 18 Celsius. So supply water must stay above that. We let go of the temptation to swing supply temps wildly during the day because slow predictable operation lets surfaces stay dry and comfortable. Now weave in storage. On the loop, we drop a stratified thermal tank, maybe 10 or 20 cubic meters for a medium building. Stratification uses simple physics. Hot water is less dense, so it floats. Cold water sinks. If we design diffusers at the tank inlets to reduce mixing, we can maintain layers 40 degrees on top 30, in the middle 25 at the bottom. Morning solar thermal can charge the top layer. Midday excess heat from the data center can charge the mid layer. Evening heating draws from the top. The tank turns erratic sources into smooth sinks. We spend precision on diffuser design, on sensor placement at multiple heights on insulation to keep stratification alive. We let go of insisting every kilojoule be perfectly layered. Some mixing is fine. Thermoclines can be fuzzy. The tank forgives us. Now add edge computing to watch over all this. Each building has a small industrial PC or a capable microcontroller-based controller. It samples temperature, flow, occupancy, humidity. It runs a lightweight model, maybe a decision tree or a prune neural net trained on that building's rhythms. It predicts at 1700 hours occupants will return. Pre-warm floors by 1 degree. raise domestic hot water by 5 degrees because showers will spike. These are inferences, and we measure them by inferences per joule. A tiny model on a microcontroller might use a few millijoules per inference. A larger model in the cloud might use joules to tens of joules, especially when transmission is counted. We spend precision on the local frequent inferences. We let go of constant cloud chatter. The building should run even if the internet goes on holiday. At the district level, a coordinator could be a server in the plant room, pulls summaries every 15 minutes. Not raw data, just aggregates current thermal load tank state of charge, predicted next hour needs, available waste heat sources. It solves a modest optimization, minimize electrical energy for heat pumps, subject to comfort constraints, storage limits, and time of use tariffs. This is classic model predictive control, but humane. We spend precision on the forecast horizons that matter: next hour, next 4 hours, if there's a storm next day, if there's a known solar lull. We let go of ultra long range forecasts that carry too much uncertainty for too little gain. And we ensure that if this coordinator fails, buildings have their own rules, their own deadbands, their own backups. Graceful cascades again. Let's pull in ventilation and indoor air quality. Each building has energy recovery ventilators with 90% sensible efficiency and perhaps 70% latent if an enthalpy wheel is used. Outdoor air comes in at 35 on a hot day. The ERV knocks it down close to indoor exhaust, say 26. A cooling coil trims the rest. Sensors track CO2. If CO2 stays below 800 parts per million, because few people are inside the system, cuts fresh air, slightly saving fan and coil energy. This is demand-controlled ventilation. Rooted in the mass balance sentence, you can read aloud V times dC by dt equals G minus Q times parentheses C minus C naught, close parentheses, where V is zone volume, G is generation, Q is ventilation flow. We spend precision on calibrating those sensors, on setting sensible minimum ventilation, on keeping coils above dew point to avoid microbial growth. We let go of constant maximum fresh air blasting just to be safe, because overventilation wastes heating and cooling and can lower indoor humidity to uncomfortable levels in winter. What about extreme days? The heat wave outside is 38 degrees, humidity is high. Our loop rises a bit, maybe to 38 supply, 32 return, because sources are hotter. COP of air source heat pumps falls maybe from 4 to 2.5. We had pre-cooled slabs in the morning using cheap solar-powered chillers, so internal loads have a head start. We temporarily widen humidity bands, allow 55 to 65%, but hold operative temperature in the acceptable zone, say 26 to 28 for lightly clothed occupants, backed by very low mean radiant temperatures from chilled ceilings. We spend precision on keeping condensation off surfaces, on maintaining ventilation for health. We let go of rigid 24-degree set points that would stress the grid. People stay safe, the loop survives, cold snaps invert the challenge. Outside drops to 0 or below. Air source heat pumps see source temperatures so low that defrost cycles and limited mass flow crank up electrical demand. Here, our stratified tank and our connections to data center or supermarket waste heat shine. We can run heat pumps in assist mode, lifting only modestly, while an auxiliary boiler, maybe biomass, maybe green hydrogen, in the future maybe simple electrical resistance for a few hours covers peaks. That boiler runs rarely. Total annual hours might be 1 or 2%. We spend precision on sizing it for resilience, on safe flue design, on integration, so it hands off cleanly. We let go of trying to make the heat pump do 100% of load under all conceivable conditions, because that would oversize it and lower its seasonal performance factor. Now let's walk the electrons and the packets. Sensors talk over a local, low-power, robust bus, Modbus, RTUB, AC, NET, MS, /TP or CAN. Building controllers talk to the district coordinator over IP. We encrypt where it matters, firmware updates, control commands that could harm if spoofed. We relax for read-only telemetry. If a temperature is snooped, comfort is not compromised. Event-driven architecture rules tank below 32 degrees loop flow, low ERV filter pressure high. Each event triggers local logic. Only summarized states go upstream. This keeps network traffic small low as radio or Ethernet energy, and crucially lets everything keep working if the fiber is cut. We spend precision on cyber-physical safety boundaries. We we let go of cloud dependence for daily breathing. Scientific measurement remains our conscience. We instrument at the right granularity, 1 thermal meter per building, 1 per major source, 1 for the loop. We measure electrical consumption of pumps, compressors, fans. We log dry bulb, wet bulb, CO2, PM 2.5 in occupied zones. From these we can compute real seasonal COP, total useful heat over total electrical input, and real fan power per litre per second, checking against ASHRAE and ISO benchmarks. If fan power exceeds, say, 500 watts per cubic metre per second, duct saw filters are too restrictive. If seasonal COP falls below 3, while source and sink temperatures are friendly, the refrigerant charge or expansion valve tuning needs love. We spend precision on these feedback loops because without measurement we fantasize. We let go of hyper-frequent polling that drains batteries and clutters storage. 5-minute or 15-minute intervals tell the truth. Let's not forget, people, a humane system tells stories. On a display in the lobby, today 41% of your heat came from server waste, 27% from solar, 12% from supermarket condensers, 20% from the central heat pump. Residents learn that their comfort is a community act. You can even show cause and effect. Because we lowered set points by 1 degree last night, we stored energy to beat today's heat. We spend precision on making that narrative honest and simple. No jargon, no hidden guilt trips. We let go of gamified pressure that shames people for using showers. Care, not coercion. Finally, turn to the grid edge. Our district system can talk to the utility or to a microgrid controller. When the grid signals scarcity, we can raise loop temperatures by 2 degrees, widen deadbands, pause non-critical loads, and prioritize hot water draws that were deferred. Because we have storage and thermal mass comfort doesn't collapse, we spend precision on mapping grid signals to safe building actions, never cutting ventilation to the point of staleness, never dropping temperatures below condensation points. We let go of perfect adherence to price signals when they conflict with health. That is the humane and humane efficiency. So when you join all this low exergy loops, heat pumps tuned for small lifts, stratified storage radiant emitters, ERVs, edge AI, tuned for high inferences per joule, variable speed pump size by Darcy Weisbach read that as delta P equals F times L over D times rho V squared over 2 and model predictive control. That is humble, not theatrical. You get a living. It murmurs in numbers, but it lives in feelings, steady warmth, fresh air, quiet fans, clear dashboards, serviceable equipment bills that match physics, not mystery. And under it all, always the same, refrain spend precision, where physics gives leverage, temperature lift, friction losses, phase change, real-time control, safety rails. Let go where the world is already forgiving. Slow room temperatures, batch telemetry, wide comfort bands, modular component. We get an ecosystem of pumps and packets and people that flows the way rivers and blood vessels do, graded, buffered, graceful. Now let's zoom right down to the energy flows you could actually measure with sensors to see what this whole humane efficiency world feels like numerically and physically. Imagine 1 block of mixed buildings, 10 small apartments, 2 cafes, a library, a bakery, and a data center in the basement. Everything is tied together by that 35-degree loop we've talked about. Each component plays its own thermodynamic instrument. The bakery's ovens reject about 30 kilowatts of waste heat during morning production. The data center, steady as a heartbeat, throws off 50 kilowatts almost constantly. The apartments need roughly 80 kilowatts of space heat on a cool evening, and the cafes another 15. It balances beautifully because what one throws away, another can use if only the temperatures are aligned. For water with specific heat, about 4.2 kilojoules per kilogram Kelvin and a flow of 4 litres per second. Call that roughly 4 kilograms per second. A 7-degree temperature difference moves heat. You can read aloud as 4 times 4.2 times 7 equals 117 kilowatts. So a modest quiet flow through insulated pipes can carry enough energy to warm the whole block. We spend precision on those numbers, pipe diameters, insulation, thickness, velocity under 2 meters per second, because friction rises with velocity squared and pump power with velocity cubed. If you want the friction story in one clear line, say delta P equals F times L over D times rho V squared over 2. A smooth polyethylene pipe with relative roughness around 10 to the minus 5 keeps the friction factor near 0.02. drop the water speed by 20% and head loss falls by roughly 36%. The pumps then loaf at lower speed, their power falling by about the cube, which is close to a 50% cut. It's the difference between a hum and a roar. The loop's insulation is also physics in action. Suppose the outer pipe diameter is 50 mm, insulation thickness 20. Thermal conductivity of the insulation, say K equals 0.035 watts per meter Kelvin, and temperature difference between pipe and soil about 10 Kelvin. The conductive loss per meter for a cylindrical layer reads clearly as Q per meter equals 2 pi times K times delta T divided by the natural log of R2 over R1. Plugging the numbers gives about 8 watts per meter. Over a kilometer, that's 8 kilowatts, lost acceptable when you're moving 100. We spend precision sealing joints and preventing groundwater intrusion. We let go of aesthetic perfection under the street. Nobody sees it, everyone feels it. The heart of each heat pump is still that compressor. Real scroll compressors at moderate lifts, say from 25 Celsius to 45 Celsius, reach isentropic efficiencies around 0.7 to 0.8. Multiply by motor efficiency near 0.95, and you get electrical to shaft efficiency near 0.7. Combine that with decent evaporator and condenser effectiveness and you land at a real COP near 4. One sentence on Mike: each kilowatt of electricity moves about 4 kilowatts of heat. A home's winter demand of 10 kilowatts can be met with 2.5 kilowatts of electrical input. We spend precision matching compressor size to load to avoid short cycling. We let go of the fantasy that bigger is always better. Part load operation is the friend of longevity. Refrigerants tell more stories. Carbon dioxide cycles can run transcritical when the outdoor temperature pushes the gas cooler above the 31-degree critical point. Efficiency then hinges on optimizing high side pressure, so the gas cooler outlet temperature is minimized. Engineers aim for mid-30s to around 40 Celsius. Propane R290 lives comfortably below the critical point and shines when the temperature lift is modest with a climate footprint that's nearly negligible. We spend precision on charging evacuation and leak testing. We let go of nostalgia for legacy refrigerants that made technicians cough and the sky warm. Inside the library's radiant slabs at 26 degrees Celsius make people feel comfortable even when air sits near 22. Mean radiant temperature combines with air movement and humidity to form operative temperature. If you need one line for the room with airspeed below 0.15 meters per second and relative humidity near 50%, an operative temperature between 20 and 26 keeps most people comfortable. We spend precision balancing surfaces so there's no cold corner radiating discomfort. We let go of hyper-tight control that toggles valves every minute. A slab's time constant is measured in hours. Patience saves energy. Humidity's arithmetic hides in psychrometrics. Speak it cleanly. Latent heat of vaporization is about 2,460 kilojoules per kilogram. Removing just 1 kilogram of moisture pulls as much energy as cooling several kilograms of dry air by many degrees. That's why dedicated outdoor air systems often split the job. One coil handles sensible cooling, a desiccant wheel or reheat loop handles drying. We spend precision where condensation risk lives: coil surface temperatures and drain design. We let go of perfect relative humidity targets because bodies tolerate a generous range. 40 to 60% is kind enough. In the control cabinets, hum the tiny brains. Each sensor node wakes every 30 seconds, reads temperature with a 10-bit converter, and transmits a small packet. Radio energy per send is about 50 millijoules. Sleep current is tens of microamps at 3 volts mere microwatts. Over a year, one node might consume less than a watt-hour, easily supplied by a coaster-sized photovoltaic patch. We spend precision writing firmware that sleeps deeply and wakes cleanly. We let go of oversampling physics, says nothing changes that fast in water pipes. Building controllers run little optimizations at around 5 watts average, 43 kilowatt hours per year, trivial beside heating loads. A simple neural inference might cost about 1 millijoule. 10,000 inferences per hour use 10 joules, around 3 watt hours per day. Say it as a metric inferences per joule are high, and keep the model's tiny 8-bit quantize pruned. The loop thinks locally and only occasionally whispers to the cloud. Noise behaves logarithmically. If one pump emits 40 decibels and an identical neighbor also emits 40 together, they read 43, just a gentle rise. A small enclosure with absorptive lining can shave 5 to 10 decibels and dropping fan speed to 70% can cut noise by roughly 6 decibels. Humans perceive about a halving of loudness for every 10 decibel drop. We spend precision isolating vibration paths, flexible connectors, rubber mounts, soft hangers. We let go of spec sheet vanity claims that promise ultra-silent at the cost of maintenance nightmares. The goal is nights where you forget the machine exists. Entropy still rules quiet. Read the exchanger line out loud. S.gen equals Q dot times parentheses 1 over T cold minus 1 over T hot, close parentheses. To reduce it, push T cold and T hot closer together. Small temperature differences, gentle transfers, wide surfaces. The same echo holds for people and comforts small emotional gradients, gentle transitions, wide tolerances. We spend precision designing for smoothness. We let go of the spiky behavior that both physics and psychology punish. Take the heat wave again. Outside 40 degrees, loop supply creeps to 39, return to 33, COP drops to about 2.8, yet thermal mass saves the day. Each apartment slab about 2 metric tons of concrete heat capacity, roughly 2 megajoules per Kelvin, cooled by 10 Kelvin stores around 6 kilowatt hours of coolth. Pre-cool in the morning, coast through the afternoon. We spend precision on predicting weather local sensors and reliable forecasts, and on shading control blinds that cut solar gains by about 70%. We let go of fighting midday peaks with brute force. The system rides the wave instead of wrestling it. During a cold spell, the COP dips. Auxiliary electric boilers engage briefly. Suppose total backup runtime is 50 hours per year. At 100 kilowatts, that's 5 megawatt hours tiny beside an annual 400 megawatt hours across the loop. That modest reserve preserves comfort and confidence. We spend precision maintaining those backups and test them monthly. We let go of the illusion that perfection means zero backup. Redundancy is mercy, not waste. Now walk the grid coupling. The utility's frequency signal is a quiet request. If grid frequency dips from 50 Hz to 49.9, we treat it as scarcity and trim compressors. One clear rule to say on mic delta P equals K times parentheses F minus F naught close parentheses. With a gentle gain, K controllers shave around 10% of electrical draw, within seconds 300 kilowatts down to 270 without occupants noticing. When frequency recovers, loads glide back. We spend precision tuning that K so comfort remains untouched. We let go of crude off schemes that cause rebound surges. The city breathes with the grid. All of this is measurable. Seasonal COP is total useful heat in megawatt hours divided by total electrical energy in megawatt hours. Flow meters report V dot. Paired sensors give delta T. Q dot becomes rho CP, V dot delta T. Every 15 minutes logs update. Simple anomaly detection looks for signatures unexpected delta T, drops air in circuit rising, pump energy at constant flow clogging, diverging supplies across similar branches of failing valve. Alerts appear locally first, because the fastest fix is the one seen by the person already in the plant room. We spend precision on these diagnostics. We let go of drowning in dashboards. The right few metrics keep trust alive. A humane system still belongs to hands and eyes. Filters slide out easily, pumps carry cast, in flow arrows, sensors use standard connectors. A simple QR code on each unit opens a plain language service page stored locally. Maintenance intervals match measured degradation, not arbitrary months. Vibration analysis warns when bearings tire. We spend precision designing for serviceability. We let go of planned obsolescence. Durability is efficiency stretched over time. When every building participates, the neighborhood becomes a small thermodynamic organism. Exergy analysis shows total destruction down by about 30% versus isolated systems. Primary energy falls similarly. If the grid's emission factor is roughly 0.3 kilograms CO2 per kilowatt hour, then for a 400 megawatt hour annual load, about 120 metric tons of CO2 are avoided. The benefit isn't abstract, it's the quiet arithmetic of matched temperatures and shared pumps. We spend precision proving those numbers, metered audits, calibrated models. We let go of marketing fluff. Real kilowatt hours saved are quieter but more honest. Physics has its poetry too. Entropy always increases, but locally we can make islands of order by exporting disorder gently. A community loop releases heat to the sky, slowly, not in violent plumes. A data network sheds bit errors as a faint warmth, not burned silicon. Efficiency here isn't asceticism, it's grace in motion. Spend precision where the equations have leverage, temperature lift, friction phase, change latency. Let go where nature already smooths for you, thermal mass, human tolerance, statistical noise. And perhaps that's the real lesson. Energy wants to flow, information wants to rest, people want to feel cared for. When we tune our machines to those truths, we get systems that last decades, that sip power, that hum like rain, instead of roaring like engines. We get humane efficiency, a physics of kindness. Now let's walk the signal one more time from the tiniest sensor, tick all the way to the city boundary, and let every step answer two questions. What does physics demand here, and what does care demand here? We'll keep the stutter because this narrator is thinking out loud, and thinking out loud is sometimes halting. Start at the sensor. A platinum RTD, say a PT1000, sits on the supply line. Its resistance shifts by about 3.85 ohms per degree Celsius. A Wheatstone bridge feeds a 10 or 12-bit converter scaled for 0 to 100 Celsius, so resolution lands near a tenth of a degree. Physics says that chasing more than about 0.1 Celsius on a water loop is rarely worth it. The fluid slosh's mounting location adds bias, time, constant, smear truth. Care says calibrate what you have so it tells the truth you can actually act on. We spend precision on an ice bath and a 2-point check, and on lead wire compensation for 3-wire or 4-wire runs. We let go of thousandths of a degree that turbulence will laugh at. That sensor speaks every 15 seconds, not every second. Physics says Nyquist sample at least twice as fast as the meaningful dynamics. A pipe segment's thermal time constant is tens of seconds. The loop's meaningful changes are minutes. Care says cut radio chatter and controller churn that buys nothing. We spend precision matching sample rates to time constants. We let go of real-time everything which belongs to stock traders, not to heat pump. Right beside it, a local loop closes, measure, supply, measure, return, compute, delta T. If delta T shrinks while load should be high flow, may be too high, emitters may be shut, or the user curve is wrong. Physics gives the sentence, you can say aloud, Q equals rho times Cp times V dot times delta T. Care gives the tactic nudge, pump speed down. First affinity laws say a small speed cut yields a large power cut. Then if delta T recovers, stop there. If not, raise a polite flag upstream that says, hey, I'm circulating but not exchanging. We spend precision on these explainable rules that tie back to the governing equation. We let go of black boxy magic when first principles already work and are cheaper. Climb one step to the building brain. It watches a handful of zone operative temperatures, a small domestic hot water tanks, state of charge, occupancy hints from CO2, or motion and the outdoor conditions. Physics asks for a predictive load, a simple RC model, where heat flow is T indoor minus T outdoor divided by R plus C times dt by dt. Care asks us to identify R and C once cleanly during commissioning by gently exciting the building over a quiet weekend and fitting the response, then to leave those parameters alone unless the building changes. We spend precision on that one identification. We let go of refitting every week. Then it negotiates comfort. If a storm is due at 1800, the building can pre-charge mass to the high side of the comfort band, say from 22 to 24 Celsius, so the slab coasts through the evening. Physics reminds us that adaptive comfort charts allow higher operative temperatures when people have been warm outdoors. Care reminds us that libraries peak late morning cafes in the early day, apartments in the evening, so different spaces deserve different bands. We spend precision matching bands to patterns. We let go of a brittle 22.0 doctrine. Finally, it coordinates with the district. Physics wants a heat balance, Care wants privacy and frugality. So the building shares intentions, not secrets. I will need about 20 kilowatts over the next hour. I can shift 5 earlier. My tank is half full about 20 kilowatt hours. That is a few dozen bytes, not a hose of telemetry. We spend precision on intention formats that any controller can pass. We let go of spraying second-by-second fan speeds at a server that doesn't need them. At the district node, the same duet plays larger. Sources minus sinks equals change in loop energy. If sources exceed sinks and the tank is not full, lift the loop from 35 to 37 and store. If sinks exceed sources and the tank is charged, draw it down and hold the loop steady. If both are tight, ask flexible buildings, slabs preheatable water to absorb. Physics frames a constrained optimization, minimize compressor electricity subject to loop bounds 30 to 40 Celsius, tank capacity and source availability. Care frames a boundary, never chase a cafe's tiny valve when hundreds of kilowatts are at stake. We spend precision on the optimizer that moves the big numbers. We let go of micromanaging a single coil. Return to the tank and sharpen the pencil. A stratified cylinder with good PUR foam thermal conductivity, about 0.023 watts per meter. Kelvin presents maybe 20 square meters of area to the room and sits 15 Kelvin above ambient. Physics says wall loss is 2 pi times K times delta T times height over logarithm of R2 over ρ for a cylindrical layer. In the usual proportions, it totals a few watts per square meter, around 7 to 10 watts overall. Care says that even doubled for penetrations, we're talking a third of a kilowatt hour per day tiny, next to tens of kilowatt hours stored. We spend precision on diffusers and low inlet velocities to protect stratification mixing. Is entropy written into our battery? We let go of chasing the last watt of wall loss. Breathe the air math. People exhale CO2, around 5 milliliters per second at rest. In a 5-person office, that's 0.02, 5 liters per second of CO2. The steady state balance you can read on a mic is Q equals G divided by parentheses C indoor minus C outdoor. With outdoor at 400 parts per million and a target of 1,000 indoors, so delta 600 parts per million, the needed flow is roughly 0.042 cubic meters per second, about 150 cubic meters per hour. Physics says that's enough. Care says add recovery, an energy recovery ventilator, to bring the entering air close to exhaust conditions and filters that respect lungs. We spend precision on right-size ventilation and clean coils above dew point so we do not grow biology. We let go of over-ventilating to 400 parts per million just because which would triple fan power and reheat. Lower the whoosh and the whine by changing flow regime. Reynolds number says it plainly, Re equals ρ times V times D divided by mu. For air at room temperature, ρ about 1.2, mu about 1.8 times 10 to the minus 5. A quarter meter duct at 3 meters per second lands around 50,000 firmly turbulent. Drop to 2 meters per second and friction falls with V squared, while noise softens at the price of bigger ducts. Physics says spend metal once save fan energy forever. Care says the quiet will be noticed every night. We spend precision on more generous ducts and gentler velocities. We let go of skinny high-speed runs that save capital expenditure and cost years of background whooshing. Do the edge, compute bookkeeping. 20 sensors per building, each sending a 30-second packet of 40 bytes, including overhead, is 80 bytes per minute, 4.6 kilobytes per hour per sensor, about 92 kilobytes per hour per building, 2.2 megabytes per day. 10 buildings, 22 megabytes per day, 8 gigabytes per year. Physics says this is trivial for a small local server. Care says compress intentions further 15-minute summaries, so radios nap and routers sip. We spend precision on edge compression and sleepy firmware. We let go of streaming raw waveforms unless we're debugging. Hold the pump safe. Cavitation destroys impellers and peace. NPSH available is static pressure over ρg plus elevation minus vapor pressure over ρg minus losses to get into the eye. Physics demands that NPSH available exceed NPSH required by a margin. Care demands a simple interlock, a suction transducer that slows the pump and shouts politely before vapor bubbles chew metal. We spend precision on that guardrail. We let go of fancy dispatch until safety is green. Respect the refrigerant. CO2 plants see 90 to 120 bar in the gas cooler. Propane systems operate more gently but with A3 flammability. Physics demands certified relief devices, sound welds, tested pressure sensors. Care demands plain words on the screen, high pressure plant safe call service, not a cryptic code that panics at 2 a.m. We spend precision on materials and checks. We let go of clever interfaces that hide the one fact a human needs. Let photovoltaics meet water honestly. A rooftop array of 100 kilowatt peak might make 400 to 500 kilowatt hours on a bright day. Physics says turning photons into heat in a well-insulated tank often beats round-tripping through batteries when the main need is thermal. Daily losses under 5% for hot water are common, while batteries 75 to 95% round trip. Care says charge the tank when the sun is generous, bump the loop a couple of degrees if you have room, or pre-cool slabs before the afternoon heat. We spend precision aligning charge windows to generation curves. We let go of insisting every kilowatt become electrons if what people need is warmth or coolth. Guard exergy like a craftsman. Running a loop at 70 Celsius gives high exergy relative to 20 degree ambient. But if the end users live happily at 30 to 40, the extra temperature lift only feeds throttling and mixing losses. GUI Stodler whispers exergy destruction equals ambient temperature times entropy generation, and big drops across dumb valves of big entropy. Physics says keep loop temperatures just high enough. Care says teach operators that good and hot is a reflex, not a requirement. We spend precision holding gentle deltas. We let go of scorched, earth set points. Tell people the truth because scientific systems fail when people resent them. A device that reads 22 while the room feels 19 invites space heaters that torch the whole efficiency project. Physics says show operative temperature and explain radiant effects. Floor warm, air cooler, you'll still feel warm. Care says use clear words, not a glossy app that lies. We spend precision on honest sensing and plain displays. We let go of animated skins and gamified guilt. In operations, listen to drift, not noise. Track return temperatures over months. If the mean creeps up, emitters are under, used or bypasses are stuck. Track pump watts at a given flow. If it rises, filters are loading or bearings are tiring. Physics says statistical process control beats hunches. Care says don't scold a building for one weird day. We spend precision on long horizon analytics. We let go of twitchy reactions. Zoom to the city edge. Hundreds of districts each with 400 kilowatts to a megawatt of thermal capacity mesh into a thermal internet. Ringed mains and sectional valves make it resilient. Wastewater plants at 15 to 20 Celsius become steady sources for heat pumps. Peripheral data centers feed in steady 35-degree water. Physics says exergy destruction falls and peaks flatten. Care says a single break won't isolate a neighborhood. We spend precision on topology that degrades gracefully. We let go of optimizing every node every second when resilience matters more. And so the duet holds from sensor to skyline. At the sensor, we calibrate, not oversample. At the exchanger, we size for small deltas, not monster lifts. At the pump, we give variable speed, not fixed raw. At the refrigerant, we choose low GWP and serviceable designs. At control, we match time constants, not twitch. At the edge, we maximize inferences per joule and let radios sleep. At the interface, we tell the truth simply. We let everything else be a little loose, a little warm, a little slow, a little quiet, because physics says it can be and people say it should be.